Angry Birds is a great way to demonstrate optimization problems in distance. Now, if we say the angle that the bird goes flying in is the theta in which something or an object is thrown, we can say that there is an optimal theta in which the bird will go the farthest. For example, about here, theta is pretty large, it's about 80. So at about theta equals 80, the bird hit the top of the tower. Okay, let's try a second time where theta equals almost 0, about 3 degrees maybe. And the bird doesn't even reach the top of the tower. Now if we put the theta, or the angle of the bird, at about 45 degrees, somewhere in there, it obviously travels further than either of the first two birds. Now the point level failed. The point of this exercise is to show that some exact point around 45 degrees is when the bird goes flying the farthest. And optimization problems helps us find that exact number.
These two equations are given. Therefore, the product of x and y is equal to 192. By solving for one variable, we get that x is equal to 192 over y. We also get that x plus 3y is equal to s. By using substitution, we get the equation 192 over y plus 3y is equal to s. By taking the first derivative and setting it equal to 0, we can find the critical point. When solved, y is equal to 8. This is the only critical point, and therefore it is the only answer. Plugging it back into the original equation, we get that x is equal to 24.
In this example, the following information is given. The farmer wants a 150 meter squared pig pen, and each meter of fencing costs $20. Here is a diagram to represent what he wants. It is a pig pen. The area of the pig pen can be represented by the equation x, y equals 150. That's solved out to one variable equals y equals 150 over x. The total cost of the fencing can be expressed by the equation c equals 20 times the quantity of 2x plus y. Now we can combine the two equations by substituting in y into the second equation. Now we can find the critical points of the equation by setting the derivative equal to 0. Once you solve that out, you will end with x equals plus or minus 5 radical 3. However, the negative answer does not work in this example because we are working with distance. Therefore, the only plausible answer is x equals 5 radical 3. Plugging x back into the original equation, you get y equals 10 radical 3. We're looking to find the maximum total volume of the inscribed cone. It is helpful to draw a diagram. It is given that the circle's radius is 2. Next step would be to let the height of the small right triangle equal z. Using this diagram, we can establish equations that relate the variables together. By the Pythagorean theorem, it follows that r squared plus z squared equals 2 squared. Solved out, that equals z equals radical 4 minus r squared. Thus, the height of the inscribed cone is h equals 2 plus z, or 2 plus radical 4 minus r squared. By substitution. The next step is to plug in the height equation into the equation of a volume of a cone. Doing so will yield the equation 1/3 pi r squared times the quantity of 2 plus 4 radical 4 minus r squared. Now differentiate the equation using the product rule and the chain rule to give you the following equation. Now, setting v prime equal to 0 will yield the answers r equals 0 and r equals 4 radical 2 over 3. These are the critical points. Now, plugging these critical points back into the equation, v of x, yields 0, 9.93, and 8.37. The 8.37, the 2 plugged into that equation is the latter part of the interval. It is evident that the correct value of r is 4 radical 2 over 3 because it yields the highest number, 9.93. Now plugging this value back into the equations yields h equals 8/3 and the total volume equaling 9.93. That is the greatest total volume of the inscribed cone.
Hurrah!
This question asks to find the value of x which minimizes the sum of the distances squared from the middle point to the other 2 points. This question asks 4 different stepped questions. A, the primary equation. B, the critical points. C, to prove that x is a minimum and the final point. And finally D, for the value of s, or the sum. Step A, the sum of the squares of the distances. To set up the primary equation, we must think of these. Step A, sum of the squares of the distances. Step 1. The primary equation can be expressed by the phrase sum of the squares of the distances. The distances are represented by A and B. The corresponding equations would be the distance formula of A, which solves out to x, and B, which solves out to equal x minus 3. The sum of these two squared terms would equal x squared plus the quantity of x minus 3 squared, which would solve out to s equaling 2x squared minus 6x plus 9. Question B is simple. To find the critical points, find the derivative of s and set it equal to 0. X solves out to equal 3 over 2. In question C, to prove that x is a minimum, we use the first derivative test. The intervals are negative infinity less than x less than 3 halves, and 3 halves less than x less than infinity, since the critical point is 3 halves. Let's plug in the numbers 0 and 2. Plugging these values into the derivative equation yield negative and positive signs, which mean that the first interval we are decreasing in slope, and in the second interval we are increasing. This proves that our critical point is a minimum, which means our final point is 3 halves 0. In question D, we are asked to solve for s, or the sum. We can solve for the sum by plugging in the value of x back into the original equation. This would give the equation 2 times the quantity of 3 halves squared minus 6 times the quantity of 3 halves plus 9. Solved out, s equals 17 over 2. That is the minimum distance that the point yields.